All right, welcome everybody. Today we're going to talk about standing waves, waves, interference, reflection, and a whole bunch of other wave characteristics. First, we need to know what exactly we're talking about. So when we say waves, what we really mean is vibrational motion. So oscillations are very important. There are many different topics in physics that are really waves, and you break them down. All fundamental particles can be treated as waves. Photons are waves. Quantum mechanics is waves. Circular and rotational motion can be described with waves. And new in the news this past year, there are gravitational waves. Objects that have a gravitational force can create waves in space-time. So what is an oscillation? So first of all, a vibration is a periodic back and forth motion about an equilibrium position. So equilibrium position meaning a rest point, that is a position where a system wants to be at rest. And periodic means it is back and forth, back and forth, back and forth multiple times. A wave is a disturbance that is transmitted from one place to another place with no actual transport of matter. That might not make sense right now, but we'll talk about it in a minute. And simple harmonic motion is vibration that can be described by a simple sinusoid function. So what is a sinusoid function? So a sinusoid function is either a sine or a cosine. So the sine function starts at 0 and reaches a height of 1 and is periodic on 2 pi. So that means every 2 pi distance, so if we have distance versus amplitude, we have every 2 pi units of distance, we follow one full cycle. And then for cosine, we start at 1 and periodic on 2 pi, we reach 1 again. So cosine is just sine with what we call a phase shift. So we'll talk about simple harmonic motion, so a very simple sine wave. A crest is the highest point of a wave. A trough is the lowest point of a wave. Equilibrium, as I said before, is a midpoint or the rest position. Amplitude is the distance between equilibrium and a crest or trough. And wavelength is the distance between identical parts of a wave. So here's a diagram of that. Here we can see that a crest is the highest point of the wave and a trough is the lowest. And we have a wavelength. So two identical points, one cycle away, will be the same length. So this is the same length as this, which is also the same length as this. And realistically, we can choose any points we want. As long as they are identical points on the wave and they are one cycle away, they will all have the same wavelength. Okay, the most important characteristics of a wavelength, like we said, is the physical length of one cycle of a wave. We use lambda, the Greek letter lambda, to represent the wavelength, and it's in units of distance, so meters, nanometers, etc. Frequency is the number of cycles that a wave completes in 1 second. So the full number of sinusoidal cycles up to one peak, one crest, down to a trough, and back to equilibrium in 1 second. We use lowercase f for frequency, and that's in units of hertz, which is quite simply cycles per second, which, since cycles is unitless, it just comes out to 1 over seconds. Period is the time it takes for a wave to complete one cycle. So it's the time. We're going to use capital T, and it's in seconds. So the way I like to think about it is frequency is cycles per second. That's right here. Frequency is cycles per second. Period is seconds per cycle. And if you thought, hey, those are inverse, you are absolutely right. Frequency is the inverse of period. So this is the normal way that we are going to see a wave function graphed. We have time on the x-axis and displacement on the y-axis. So a period would be the time that it takes to travel one full cycle. So in this case, it's represented simply as t. So 1/2 of that is 1/2 t. And then we follow it again. We see we have a full 2 periods for 2 full waves. All right, so 2 full waves. We hit a crest, trough, and back to equilibrium. Then we hit a crest, then a trough, and then back to equilibrium. And like I said, frequency and period are inversely proportional. So frequency is 1 over period, and period is 1 over frequency. Cycles per second and seconds per cycle. So if a wave completes 1 cycle in 2 seconds, what is its frequency? So we want frequency is cycles per second. So we get frequency is 1 cycle per 2 seconds. So that gives us 1/2 cycles per second. And the unit of cycles per second is hertz. So we end up with 1/2 hertz, and that is B. Okay, if a wave oscillates at 20 hertz, how long does it take to experience 40 cycles? So why don't you pause this for a second, try to work it out and come up with an answer, and then start it when you have an answer. All right, you should have an answer by now. So let's figure it out. We want, well, first of all, how long? What we want is time, right? We want time. So we're going to start with frequency equals 20 hertz. That is 20 cycles per second. And if frequency is 1 over the period, that means that the period is 1/20th of a second. So we want 20, we have 40 cycles, and we have t is 1/20th seconds per cycle. So if we multiply that by cycles, we see we have period is 1 over 20 seconds per cycle multiplied by 40 cycles. We get 40 over 20, which is 2 seconds. That's B. Okay, so if we have 20 cycles per second, that means it takes 2 seconds to experience 40 cycles. Okay, so the speed of a wave. Wave speed is found by multiplying wavelength by frequency. So that's wavelength multiplied by frequency. We can see that we have speed is meters per second. Wavelength is in meters. Frequency is in hertz, which is 1 over seconds. So the units work out perfectly. So wavelength times frequency. So let's check it. A wave experiences 50 cycles per second. That's 50 hertz. If a wave has a speed of 2 meters per second, what is the wavelength of the wave? So go ahead, pause this, come up with an answer, and then we'll come back. All right, so you should have an answer by now. Let's figure it out. So what is the wavelength of the wave? We want wavelength. We know that frequency is 50 cycles per second. 50 hertz. And the wave speed is 2 meters per second. So we know that wave speed is frequency times wavelength. That means that wavelength will be speed divided by frequency. So we have 2 meters per second divided by 50 hertz. That means the wavelength is 1/25 meters. So if it travels 2 meters at 50 cycles a second, our wavelength is 1/25 meter. And that is that. So one characteristic of waves is that they have to propagate through a medium. The wave can't exist without something for the vibrations to move through. That means that there has to be stuff that the wave is moving through called a medium. A formal definition is a substance that makes possible the transfer of energy from one location through another, especially through waves. And some examples of this are, if for sound, the medium is air. For a water wave, right, the ocean, the medium is obviously water. And you can have other types of waves as well. Electromagnetic waves are a special case. They can move through a vacuum, but they create their own medium. They are a self-propagating wave, and we'll probably talk about that at some point in the future. There are two types of waves. Transverse waves are when the motion of the medium is perpendicular to the direction of the wave. So that means if the wave is traveling in this direction, the medium is traveling in the vertical direction, so perpendicular to the direction of the wave. So that's strings on musical instruments. We can see that if we have a string here, if you pluck it, you pluck a string, you get this type. So the string is moving in this direction. You also have longitudinal waves, where the motion of the medium is parallel to the direction of the wave. So one example of that would be sound. We're going to see a good image of that in a minute. So that would be if the wave is moving in this direction, the medium is oscillating back and forth in that direction. So a good example of this is with a slinky. So with a slinky, you can create a transverse wave where you can picture the coils. They're moving in an upwards and then a downwards direction. So these are the pulses are moving up and down. And you can also compress a slinky. So here we can see that from here to here, the coils of the slinky are a lot closer together than from here to here. So that compression wave would be moving in this direction. The compressed part would be moving in the direction that the wave is moving. So a wave function, a simple harmonic motion wave can be described by a sinusoidal function, and we need to make it fit, essentially. We know how to use a sine wave. A sine wave has a height of 1 and a period of 2 pi, okay? But waves have an amplitude a, so a height of a, and a period of t. We need to fit the sine function to the wave so that if you graphed, like if you took experimental data and graphed that sinusoidal wave, we would need to include the amplitude and the period into a normal sine function in order that if we graphed it on a graphing calculator, those two waves would look the same, the experimental data and the graphing calculator. So we start with y is sine of x. And the first part that we can see is the most obvious to modify this wave is that we have a height of a instead of 1. So if we start with y, essentially you can write this as y equals 1 sine of x. Well, we can multiply it by a. So multiply the whole function by a. We end up with y equals a sine of x. Now, we can swap out these variables to make it fit the physical quantities that we're measuring. So instead of x, we have time, which we're going to write as lowercase t. And instead of y, we have displacement, which annoyingly enough is usually called x. So it's a distance or a displacement. So what we're going to end up with is x equals a sine of t. Now we know that sine is periodic on 2 pi. That means it has a domain of 0 to 2 pi. However, the period of the wave is capital T. So what we want is we want this function, this wave function, to go from 0 to t. That's what we really want. So we want it to go from 0 to t. And what we can do is we have to have 2 pi in here, because say that the period was 2 seconds. If we used a normal sine function, 0 would be fine. But if we put 2 seconds in, that is so if we were going to start, we're going to graph a normal sine function. 0 is fine, right? But, okay, so t over 2 is 1 second, sine of 1. So let's see, we have sine of 1 is somewhere, if we're doing a unit circle, here's pi, so that's 1, 2. Okay, so sine of 1 is somewhere around here. So we would end up with kind of this region, maybe, as opposed to here, back on the equilibrium position that we would need. And then if we got to 2 seconds, we're still not even back at equilibrium, where sine of 2 is around here. So these functions we're not getting what we want out of it. However, there is a rather simple modification that we can do. How about we do this? Let's think about this. What does the time variable over the period represent? Essentially, this is a fraction of the period. So as we go along the time axis, we are going to get fractions of the full period, which means that we will cycle through integer multiples. So we're going to cycle through integer multiples. So basically, as we go along in time, we are going to get, 1, 2, 3, 4 every period. So when we hit a full period, so we get t over t, that's 1. So that is a full cycle, except for sine, a full cycle is 2 pi. So if we multiply these two together, what we get is 2. So if we take 2 pi multiplied by t over the period, what we will get is this cycles through integers multiplied by 2 pi. So we're cycling through multiples of 2 pi. And that's what we want. That's what we want. The sine function to cycle through multiples of 2 pi, and it will graph this appropriately. So what we end up with is we have the displacement is the amplitude multiplied by sine of 2 pi time over period. And so what this means, if we put this into a graphing calculator and we compare the graph that it generates to any experimental data that we would take of a real oscillation, those two graphs would look the same. This is called curve fitting. But all you need to know is that this is how we represent a real oscillation in a graphical manner. So A is the amplitude, T is time, so lowercase t is time, capital T is the period, and I pretty much said that last sentence down there. But t over period will cycle through integers, so we have cycled through multiples of 2 pi, which is the domain That is what sine takes as acceptable input. So to work from a graph to an equation, this is very simple. So first what we need to know is that we have x equals a sine of 2 pi t over t. We have, first of all, an amplitude of 20. So that means we have x equals 20 sine of 2 pi t over t. And now we need the period. So you can see that we cycle through, okay, we're up to a crest, equilibrium, down to a trough, equilibrium. So the period is 2 seconds. So we have t time graph here, that's 2 seconds. That means we end up with x equals 20 sine 2 pi t over 2. And you can simplify that 2 and 2. This graph is x equals 20 sine pi times time. So if you put this, if this was experimental data that you were measuring actual displacement versus time, and then you put this into your graphing calculator, those two graphs would match. All right, now working from an equation to a graph. Okay, let's do this. So first, amplitude. Let's make our graph here. So we have time and we have displacement. So we just know that this has to be 2.5. And our period, which we find here, is half a second. So let's just delineate some different points on this graph here. Let's make this 0.25. Let's make this 0.5, 0.75, and 1. All right. So that means we have to go through a full cycle in a period. So that means we have to hit a crest and a trough. If we see, we kind of fudged it a little bit, but that is essentially what we need. Extend that out here. Hit a crest, hit a trough. There we go. That's 2 full cycles. How do we do this? We found the amplitude and the period, and we drew a graph. Okay. So what creates oscillations? What is the driver of oscillations? So in order for a system to oscillate, there has to be a force opposite to the direction of motion. Okay? There has to be a force opposite the direction of motion. As we move past the equilibrium position, the direction of that force changes. Picture a spring system. Picture a spring system. As the spring moves, so a vertical spring like this. Let's all draw it. So vertical spring, and let's say here we have a mass. Right? As the spring moves down, it stretches the spring even more. We know that when we stretch a spring, the force that it exerts is in the opposite direction. That is the restoring force. As we stretch the spring down, so as we move in the downward direction, the restoring force pulls up. Okay, for springs, we use Hooke's law. That's the force. Force is equal to kx, where k is a spring constant and x is the distance that it's compressed. The force of a spring increases as the spring stretches, and it accelerates the mass in the opposite direction that it is moving, always. So we can stretch or we can compress, but whichever direction we are moving, if we have a spring system here, as it moves this way, the force is going to be pulling it that way. As it compresses the spring, as it moves this direction, it's compressing the spring, so the force exerted will be in the opposite direction. When you compress a spring, the force is in the opposite direction. So whichever direction you're moving, the restoring force is in the opposite direction. Okay, so pendulums. Pendulum is also a simple harmonic oscillator. You can picture a pendulum moving. It moves about the equilibrium position, the bottom position, okay, in a periodic manner. It occurs on a set time schedule, time scale, whatever you want to call it. So if we're going to draw a pendulum system here, we have our equilibrium position, then we swing up, and we end up over here, and then we swing down, and we swing up the other side, and then we end up over here. So the restoring force is always gravity. The restoring force is always gravity. As we move up, okay, we have gravity that is pulling down. Gravity is pulling down. It wants to return us to this position. The force of the string or whatever it is hanging on, right? This right here, this string will pull it in this direction. So one component in one direction, one component in the other. But the result is a net force that pulls it back to this equilibrium position. What is going on here? All right. So if there's anything that you need to take notes on, it's this. If you are in AP Physics 1, these two things are on your formula sheet. However, you do need to know what they mean. There's no point in having a formula if you have no idea what the variables mean. So for spring mass systems, so a mass attached to a spring, okay, and pendulums, the period of the oscillation is an inherent quality. Like things that have mass have a certain amount of mass because that's just the amount of mass that they have. Okay? So springs, the period of a spring mass system is 2 pi square root of the mass attached to the spring over K, the spring constant. Pendulums, the period is equal to 2 pi times the square root of the length of the pendulum divided by gravity. So as the mass increases of a spring mass system, the period increases. As the spring constant increases, the period decreases. And interestingly, for a pendulum, the only thing that you can control to control the period of a pendulum is the length. The mass attached to the pendulum does not matter, interestingly. And also, the height that you bring it to does not matter. So if you had a pendulum and you brought it up to here and released it, and brought it up to here and released it, these would both have the same period. You can test that if you want. Okay, so what happens when two waves encounter each other? What happens when two waves suddenly hit each other? Well, they have to sum. So the amplitudes at each individual point will sum, they will add together to find a resultant wave shape. What does that really mean? Well, for instance, you can have constructive interference. Constructive, construct, build. So we see we have wave 1, which has an amplitude x, and wave 2, which has an amplitude x. These are identical waves. They have the same period. Okay? And if we put them on top of each other, the amplitudes at this point, drawn by this black line, if they're right on top of each other, they add to give you a higher crest of 2 times x, the sum of those two amplitudes. And you also get down here, you get a trough that is also of amplitude 2x. Pretty straightforward. When they're right on top of each other, they sum, they add together. Okay, you also have destructive interference, where if these waves are shifted off by a half of a wavelength, we have a crest of height x and a trough of height negative x. And those two, if we put them right on top of each other, they sum to 0. You also, over here, you have negative, you have a trough, and then you have a crest. But also, somewhere halfway in the middle, okay, we have some, we're descending, we're coming out of a trough, right? We still have some negative amplitude, but here we have an equal positive amplitude. So the result is a flat line all the way through. However, most waves are not like this. You have something called complex interference. So on top we have wave 1 that has a pretty tall amplitude and a long period, right? A long wavelength. Okay, and then we have a shorter wave, which has a smaller amplitude and a much higher frequency, so a shorter wavelength. Okay, if we add those point to point, we have this one has some positive amplitude, this one has some a little bit less negative amplitude, but if you add them perfectly, you end up with some still positive. All right, let's look at what this peak is right here. Well, we have some positive, and we have a maximum positive, so those we have a little bit of positive and a lot of positive, so they add. But the point being that we have a weird wave shape. We have a weird wave shape. Okay, we can see that it's still sort of, if we look at the, if we squint our eyes, we can see that it kind of still follows this sort of pattern, right? But we've added this weird wobble to it, this weird wobble. Okay, so when they sum, the amplitudes at every point add, so you get some weird looking waves. All right, so two wave pulses are traveling towards each other. Okay, figure out what they look like when they reach points x and y. So when they are both right on top of each other at point x to y, what is that shape? So pause, take a minute to figure it out, and then resume. All right, so if you start it up again, let's figure it out. So my strategy for this is always to put them right on top of each other and just figure out what's going on. So let's draw the one on the left here. That's a good representation there. And then let's draw the one on the right. Go down, up. All right, yeah, pretty good. Let's add them together. So let's take this first point. 0 and 0 gives us 0. Great. We have some positive and some negative, gives us pretty close to 0. We have a crest and a trough, that gives us 0. We have a positive and a negative, that gives us 0. And so on, and so on. So the correct answer is B. Correct answer is B. So by putting them right on top of each other like that, it's very easy for us to figure out what that result wave is going to look like. Okay, so when waves encounter boundaries, what happens? Well, they reflect. When, the wave hits something, it doesn't just disappear unless it's a very special material that it hits. If it's a solid thing, it's going to reflect. So we have two different types of reflection. So at a free boundary, that's over here on the left. So if we have a rope, let's say, and we tied a loop around a pole, it will reflect and not invert. So it will reflect in the exact same pattern. We send it, it has some positive amplitude, and it comes back with a positive amplitude. So we're moving in that direction. First we're moving towards the pole, and we're moving away from the pole, but it's still positive. So at a fixed boundary, which would be this wall over here, waves are reflected and inverted. They are inverted. So we have some positive amplitude traveling towards the wall. It hits the wall. We have a momentary flat line. And then we end up with an inverted wave. So we go from a positive amplitude to a negative amplitude, moving in the other direction. So standing waves. So what happens? How do we get standing waves? Essentially, we have to think about a reflection. So at a fixed boundary, let's say, we send a wave. We're going to send a wave with, let's say, that. The reflected wave will look like that. So if we keep sending this wave and we keep getting a reflected wave, keep sending the wave, keep getting a reflected wave. Eventually, we get this what's called a standing wave pattern, right? And if the medium, however, has to be an integer or half integer multiple of the wavelength if it is a fixed boundary at both ends. And we'll see how that works out in a second. So first, we need to know the minimum points. The minimum points where the amplitude is 0. These are called nodes, all right? And the maximum points, those are called antinodes. Antinodes. Okay, so like I said, so for a situation with two fixed boundaries, we only have certain standing waves that are allowed to exist. So we have to have, at a fixed boundary, the amplitude must be 0. So at a fixed boundary, the amplitude must be 0. So here and here. So at the walls, we have to have fixed 0 amplitudes. So what this means essentially is that these are standing waves that will naturally occur. So if you send a wave with this wavelength, a standing wave will happen. If you send a wave into this container that has this longer wavelength, a standing wave will not occur. You won't get this nice shape. You will have a very complex, non-pretty looking, I suppose, shape of a wave. So we have to fit a certain number of waves into this boundary. So sound is a wave that travels through what's called a matter medium. So it can be air, it can be water, it can be solids. Sound also moves through the ground. And interestingly, sound moves a lot faster through the ground. That's why if you were sensitive enough, animals actually have very sensitive feet. They can usually feel things approaching before the sound of them actually gets to them because the sound is traveling through the ground. However, back to sound in our day-to-day lives. Well, sound is a longitudinal wave. It's called a pressure wave. The molecules oscillate back and forth. The air molecules oscillate, and the energy of the wave hits your eardrums. We can hear 20 to 20,000 hertz. That is the maximum and minimum frequencies that we can hear. However, our normal day-to-day sound range is within the single thousands, if memory serves. So sound propagates in 3 dimensions. So that means sound is non-directional. You can talk with your back turned to somebody and they can still hear you because the sound travels in a 3-dimensional way. So in all directions, forward, backward, up, down, side to side, etc. And the speed of sound in a medium is determined by the density of that medium, so the temperature and things like that. So speed of sound in liquids and solids are generally higher than in gases. So we have an animation here that we're going to watch that is a visualization of how sound moves in air, or really any medium. So let's pay attention to what we have here. We have these denser regions. We have these denser regions where the molecules are closer together. Over here, this would be, say, our speaker. And let's just see what we see. So you can see, if we choose, right, let's follow this pressure wave along. The compressed part travels. So if we pick one, right, as we pulse, we can see that this, right, we're following. So that would be one wave, right? That would be one high density. So this pressure, so we're pushing the air molecules, and they are essentially smacking into the air molecules in front of them. which are then smacking into the air molecules in front of them. Let's watch that again, and let's pick one air molecule. Let's pick this one. Well, it moves back and forth, back and forth, back and forth, back and forth. Moves back and forth and back and forth and back and forth. So that air molecule does not go anywhere. That air molecule stays right in this general region. It just oscillates back and forth, back and forth. It doesn't go anywhere. However, we know that a wave goes all the way the length. And that's an interesting thing about sound. And really any wave, the medium does not change, but the wave travels. So beats. Beats are something that can occur in sound when you layer two different sounds on top of each other that are not the same frequency. So if they're very close in frequency, but they're not exactly the same, then you can get what's called beats. So we have on top here, we have 110 hertz, and down here we have we have 100 hertz and 110 hertz. And if you look at the waveforms themselves, they don't really look that different. However, when you superimpose, when you see what happens to their constructive and destructive interference, when you add them point by point, so it would be kind of hard for me, so take this point and this point, and some other point in there. You add them, you get this waveform, this very interesting looking waveform. And what is interesting about it is that it has its own wavelength and period. So you add them together, you get a wave that has its own new wavelength and period. Fascinating. It's really fascinating. It's really interesting to hear. I highly recommend that you search out some examples of beat frequencies. And if you subtract, you find the difference between those two initial frequencies, frequency 1 and frequency 2. So there's a difference of 10 hertz between them. So the frequency of this new overall wave shape is 10 hertz, and that's what a beat is. So resonance. Resonance is a phenomenon that occurs, it's standing waves. So you can get multiple standing waves within the same size of container, let's say. So, we have two walls here. So the fundamental is essentially the simplest wave that can exist in a particular container. It's the simplest wave that can exist. And it has the minimum number of nodes, So the fundamental is the minimum number of nodes that you can have. So for a string that's fixed at both ends, the string must be an integer or half integer of the wavelength. So if you drive the wavelength with some frequency, the wave has some natural speed, the wavelength is what matters about whether or not it's going to create a standing wave. Remember those diagrams previously where we had these weird looking standing waves that can't occur? So the wave, in order to create a standing wave, we have to have a very specific wavelength that relates to the container that it's in. So resonance, we can get, these are all possible standing waves within the same container. We have the first, second, third, fourth, fifth, and sixth. So we have one antinode, we have two antinodes, 1, 2, 3 antinodes, 1, 2, 3, 4, and so on. So these are all possible within the same distance, just at different driving frequencies. So for a closed tube, we can get resonances as well. For a closed tube, we can get resonances. So at the closed end, say you have a speaker that you are driving, you are pushing air into that speaker, you can get pressure that builds up, So if you were to graph here, so here is a here's a distance along the tube, and this would be, say, the displacement of air. So where the very, very high pressure is, that air cannot move. However, at the open end, the air can move a lot. So you have an antinode, right? So we would end up with a wave that looks like this. So what does this mean? Well, we can have multiple types of standing waves in a closed at one end tube. So here we have the closed end. So here's the closed end. We have a high pressure, low air displacement. Okay. All right, and if this was pressure, right, then this would be the opposite way around. However, we don't have to have just this simple one. We can have more than one type of wave. So here we have another node. So this one has two nodes. Okay, this would be a high displacement area. You'd go back down to a low displacement and then another high displacement area. So if we took a particular frequency, say we had a speaker over here, whatever, and we were pumping air, right, in a sound wave into this, if we hit this correct frequency, we would get a nice standing wave, and it would resonate, and it would be nice in this tube, essentially. So one weird thing about resonance occurs at the frequencies that work. Think about a boom whacker that we might have played in class with. So it's just a plastic tube that's open on both ends. If you just randomly smack it, it makes a sound. That doesn't really seem to make a lot of sense, but because we're not driving it with any particular, we didn't put a speaker on the end that was giving it a particular frequency. However, when you whack it, when you hit it, the tube itself vibrates. And when the tube itself vibrates, it creates a whole bunch of different frequencies of pressure, like this, like these. And the ones that are a nice integer multiple, right, that create a nice standing wave inside the tube, those are going to be the ones that get amplified that you hear. So this is an open tube, and we have a closed tube just to compare the two. So one that's open on both ends. You see that we're open on both ends here. So the point about closed at both ends, open at one end, or open at both ends is a closed end must be a node, and an open must be an anti-node, or a. And that just helps you to figure it out. So we must have a minimum of one node. We have to have a minimum of one node for it to even be a wave. But from that one node upward, we can figure out the multiple standing waves that are possible. So in our open tube here, we see that we have the simplest one, has one node right in the middle, and two antinodes at the ends. Okay, for what we call a first overtone, we have two nodes, and we have 1, 2, 3, 4, 5, 6. We have 1, 2, 3 antinodes, etc., etc. So these are all possible waves that can exist in these tubes. So this is the same tube. This is the same tube, but all of these waves are possible inside them. And then down here we can see we have multiple types of standing waves in those closed at one end. So if you really want a formula, this is for a closed at both ends. The length, so we count up the number of harmonics. So the harmonic, a first harmonic is n equals 1. This n equals 1, and that is the number of full loops, I think is a good way to think about it. So this is one loop, which is half of a wavelength. And so this has 1, 2, 3, 4 loops. If we were to trace out a wave, we'd have a peak and a trough. That's one wavelength. And then a peak and a trough. That's another wavelength. If we look at this one up here, we hit a peak and a trough, and that is one wavelength. So if you really want a formula for a closed at both ends, string or tube or whatever, the nth harmonic, so the number of loops, the length of the tube is going to be equal to that number n over 2 multiplied by the wavelength. So let's practice with standing waves. The speed of sound in air is 340. Determine the fundamental of a closed at one end air column, an open at one end, and a closed at both ends. So the very first part of this, why don't you give it a shot, take a pause, see if you can draw it. So let's put out our let's make our 3 tubes. So we'll have one that's closed at one end, closed at one end and open at one end are the same thing. I mistyped. So we have closed at one end, open at both ends, and closed at both ends. So see if you can draw the standing waves that would occur in those, and then, all right, so you should have drawn your standing waves, and now we're going to see if we can find the frequency. So let's draw this first one. So at a closed end, we must have a node. So we're going to put those there. At an open end, we must have an antinode. So I'm going to put those there. There. And then we have to have at least one node in it for it to be, so we're going to put that right in the middle. And now let's draw. So we go from node to an antinode, node to an antinode, node to an antinode, and then up and there and there. So those are the 3 types of standing waves that we can get. So let's figure out, these are all the same length. All the same length. Let's figure out how many waves we're fitting in. So for let's start with the first one. So we go from a node. Nope, don't do that. We go from a node to an antinode, and then if we were going to follow it, we would go down, and that would be a half wavelength. Down, and then up, and that would be one wave. So what it actually is as it turns out, this length is 1/4 the wavelength. This length over here on the second one, we see that we go from the base up and here. So we go from a trough to a crest, and we know from a trough to a crest is 1/2 of the wavelength. And for this third one, we go from equilibrium to a crest back to equilibrium, which is also 1/2 of the wavelength. If we were to continue this, we would see we go up to a crest, then down to a trough, and then back up for a full wave. So that means that in this case, the wavelength is 4L, wavelength is 2L, and the wavelength is 2L. Velocity, 340, is frequency times wavelength. So that means that frequency is velocity over wavelength, right? Velocity equals frequency times wavelength. Frequency is velocity over wavelength. Yes, okay, great. That means 340 divided by 4L. So 4L, we have 0.675 times 4 equals, so 340 divided by 2.7. So that means the frequency would be 125.9 hertz. And it is very simple to see that these would just be twice the frequency if that's not obvious. Let's do it out. So we have frequency is 340 over 2L, and that would just be twice this original one. So the length is 0.675 times 2, 340 divided by 1.35. That is 251.85-ish hertz. All right. Harmonics. What are harmonics? Well, harmonics are multiples of the fundamental frequency, and you can have multiple harmonics within the same sound wave. So let's see if we can find an example of this. So we start with the baseline, this green one right here, this green one right here. So I'm going to keep tracing it out. Okay. That is the fundamental. So within this length, that is our fundamental. That's our first. We also have this orange one, which is the third harmonic. So we can see that we fit 1, 2, 3. So we get, well, 1, 2, 3 in what we would get one wave out of in the first case. And when we add those together, point by point, what do we get? We get this weird, funky looking third waveform that is a combination of the first two. So when we add harmonics on top of each other, we get unique waves. What's a consequence of this? Well, different instruments sound different. So if we look at these, first we have a tuning fork. So if we were to trace out the wave, it would look like that. A flute, if we were going to trace out the wave, we get this kind of very similar waveform. A violin, oh, I can't trace worth a darn. And then a singer, you get, yeah, I can't trace at all. Anyways, you can see that if these are all the same, these are all supposedly the same note. Supposedly, well, they are. They are in tune with each other. I don't actually know what note this is. I'm sure we could figure it out. Maybe it might be A440 or something like that. But we can see that the fundamental, so the fundamental frequency that this is based off of is the same. They have a very similar oscillation pattern. But if we were to break down the amplitude of these, so this is the important point. We have a very large amplitude of the bass sign, so the first harmonic, and a smaller amplitude. So here we have a very large amplitude, and here we have a small amplitude. So if we were to graph this, this would be called the spectrum analysis. So for a tuning fork, we can see that this frequency, right, this baseline frequency has a very high amplitude. We also get this baseline frequency in the flute, in the violin, and in the human singer. There may be a little bit, my drawing skills, of course, not on point. But we can see that, okay, let's take the flute, for example. We also have a lot, so a high amplitude of the second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic, where for the tuning fork, we have a much lower amplitude for these harmonics. For a violin, it's very interesting. We get lots of peaks in the higher and higher and higher frequencies. And in the human singer, it's actually very interesting that the peak of the second harmonic and the third harmonic are greater than the fundamental. We still hear it as the fundamental, but we get these high peaks of these higher frequencies. And so these are all the same fundamental frequency, but they sound very different because of the amount of the higher frequencies that are added on top of that original waveform. So overtones, they are when two notes produced by an instrument, they have the same harmonics. The harmonics with the highest amplitudes will constructively interfere, and you will hear that note amplified. So